In the previous lectures, all of our regularization techniques were based on the premise of supervised applications. In this video, we will discuss the problem of regularization in unsupervised applications. In particular, we will look at three types of autoencoders. These are the denoising, the contractive, and the variational autoencoder. As we'll see in this lecture, regularization in unsupervised applications often has specific applications in which we are trying to learn representations with specific properties. The goal of the regularization is to therefore force the hidden representation to create features with these specific types of desired properties. We often hear about overfitting and regularization for supervised applications, but we often tend to hear less about the issue of overfitting when it comes to unsupervised applications. This is not a coincidence. The reason for this is that there is always a greater tendency to overfit in supervised applications. In supervised applications, we are often trying to predict a single bit of target data. So for example, if we have a binary class label, we are trying to predict a single binary class label from each training instance. On the other hand, in unsupervised applications, we often try to learn a lot more intricate information. Often we try to learn the entire distribution of the data, in which case the target data corresponds to all dimensions in the data set. In other words, for the same number of records, the amount of target data in terms of number of bits is a lot more. So overfitting tends to occur less often in unsupervised applications as compared to supervised applications. The goal of regularization in unsupervised applications is often to provide specific properties to the reduced representation. In the case of autoencoders, note that the dimensionality of the hidden layer controls the tendency of overfitting. If your hidden layer has a very high dimensionality, there is always a risk that the autoencoder will simply copy the input from one layer to another. So regularization of autoencoders often uses a large number of hidden units, and therefore these are considered over-complete autoencoders. However, by adding regularization to the process, we force the hidden layer, the representation in the hidden layer to have certain types of properties. So the first application of autoencoders is that of sparse feature learning. So imagine that you had an autoencoder in which you used a larger number of hidden units than the number of input units. However, you want these activations to be sparse. What I mean by sparse is that for any given input, most of the hidden nodes will take on a zero activation and only a small number of nodes will take on a non-zero activation, which basically means is that for each data point, you will have a high dimensional representation, but only a small number of non-zero values. This is a typical kind of representation that, for example, the bag of words representation of text has. So this is a sparse kind of feature learning, and sparse feature learnings have their own applications in various domains such as image data. The way in which sparse features are learned using autoencoders is that you use a larger number of hidden units than the input unit, but you add L1 penalties to the hidden layer. As we discussed earlier, L1 penalties tend to encourage sparse activation. And the changes to the backpropagation algorithm are quite modest in that the only difference is that now you have to add the additional effect of the L1 penalty to the backpropagation algorithm. So the backpropagation algorithm proceeds as usual, except that it picks up the flow from the penalties from the hidden layer during the propagation. Now, another way in which performing sparse feature learning is what you call a top K encoder. So here what you do is that you use only the top activation in the hidden layer. So when you forward propagate any activation which is not in the top k, you set it to 0. And similarly, during back propagation, you back propagate through only these top activations. Now note that this type of approach essentially behaves like an adaptive ReLU, a ReLU with thresholds that depend on the activation for the training instance. So really the training process is not very different from the ReLU, except that when you back propagate only through the top activation. Now, a second type of autoencoder, a second type of regularized autoencoder is what is called a denoising autoencoder. And this is very useful for denoising applications such as cleaning up corrupted data. And in order to train a denoising autoencoder, we do need examples of good inputs. But what you do is that you add noise to the input representation. Now, the kind of noise you add to the input representation can also depend on the kind of insight you have about the typical kind of corruption that your data might eventually contain, that your test data might eventually contain. But certain types of noise are more useful than certain types of input. So for example, for real value data, you will use Gaussian noise, and then you can use masking noise for binary data. In the book, I discuss the different types of noise that can be added. There's another kind of noise that is discussed there, which is called salt and pepper noise. So you have these noisy inputs, the noise is synthetically added to the input, but the output is the same clean data set. So now normally in the autoencoder, the output and the input are the same. Here, your input is noisy and the output is a clean representation. And then you train this autoencoder, and one can show that when you add Gaussian noise, if you have a single layer autoencoder with linear activations, then Gaussian noise essentially results in L2 regularized SVD. So here I have shown an example of the workings of a denoising autoencoder. So below I have this two-dimensional, imagine you have two-dimensional data. This is just a simple way of, usually you will have very high dimensional data and you will have a low dimensional manifold, but here I have shown a one-dimensional manifold for two-dimensional data. Now, the data points are actually distributed along the manifold, as shown on the right, lower right. This is how the data points are truly represented. But because you added noise to it, typically they will move away from the manifold. So what does this really mean? You have basically corrupted your data. So for each data point, so for example, if you had image data, each of these little stars over here, it now becomes a blurry image. And the more far away you go away from the manifold, the more blurry it gets. It becomes, at some point, the data point becomes meaningless. That image won't have any meaningful pattern remaining. So, but when you add a small amount of noise, it just creates a more blurry image, and the autoencoder, so the way you train it, you will be giving it inputs of blurry images and outputs of sharp images. And what the autoencoder learns, is that the sharp images, they occur on a certain manifold. It learns that if I have data points which are away from this manifold, it learns the nature of that manifold. It learns that I need to project that point somewhere along that true manifold, that low dimensional data distribution along which the point lies. So a second variation of a similar idea, which is called gradient-based penalization, which is called contractive autoencoders. Now, in contractive autoencoders, again, you do not want the hidden representation to change very significantly with small random changes in the input values. So the idea here is that when you have a data distribution in high dimensional space, often what happens is that the true manifold on which all the data points lie, it's a much lower dimensional manifold as compared to the dimension of the data set itself. So if you look at most random directions from the manifold, if you pick any random direction, typically it will be perpendicular to the manifold. So what you do is that you use a regularization term which tends to selectively damp the component of the movement perpendicular to the manifold. Now the regularization, it damps in all directions, but it doesn't face any resistance in orthogonal directions to the manifold. Now one point that you have to understand is that what you are trying to aim for, you're trying to aim for a hidden representation which doesn't change very significantly with small random changes to the input values. At first sight, this might seem like an unreasonable goal. After all, for a given input, you want to reconstruct the input. So obviously, if you change the input, your output also has to change. But the point here is that when you have the data distributed along a low dimensional manifold and high dimensional data, most of the changes which do not occur along that manifold, they are irrelevant. It is these changes that we want to damp. So how do we achieve this goal? The way we achieve this goal is that you have a loss function which contains two components. First is the reconstruction loss that is given by equation 3. So assume that xi hat is the reconstructed version of the ith dimension and xi is the original input for the ith dimension, and this is the sum of squared loss. There are other loss functions that are used. And the regularizer here is the sum of squares of the partial derivatives of all hidden variables with respect to all input dimensions. So what is this? This is basically the Frobenius norm of the Jacobian. So if you have the input and the hidden layer with respect to the input, you can create a Jacobian, and you're taking the Frobenius norm of that entire Jacobian matrix. So here what you have is that you have k hidden units denoted by h1 through hk, and you're taking all the partial derivatives with respect to all the d inputs. Now when you perform this, you want to optimize L plus lambda R, where lambda is your regularization parameter. And one of the interesting results that you can show is that if you use a single linear layer, it leads to L2 regularized SVD. Now this is similar to the denoising autoencoder. Note that a few slides back, I showed that if you had a single layer autoencoder with linear activations and adding Gaussian noise to the input results in L2 regularized SVD. So essentially the contractive autoencoder and the denoising autoencoder, they are achieving the same goals in different ways. The denoising autoencoder is achieving this goal by adding noise to the input, whereas the contractive autoencoder is achieving this goal by penalizing the hidden layer. So just to see the similarity between these two types of autoencoder, I have shown a diagram here. So in the case of denoising autoencoder, when you add noise, you get all these data points which are a little bit away from the true manifold, and typically they'll be projected to their nearest point on the manifold. And when you have a high dimensional space and a low dimensional manifold, typically this nearest point on the manifold, it will be perpendicular, the direction. And similarly, in the contractive autoencoder, if you look at the figure on the right, when you perturb it in a random direction, most random direction will be roughly perpendicular to the manifold. So it will change only a small direction along the manifold. So you only care about the change that occurs along the manifold, because those are the only meaningful changes which are consistent with the data distribution, and movements which are inconsistent with the data distribution are damped. This is true both for a contractive autoencoder as well as for a denoising autoencoder. So in that sense, the contractive autoencoder and the denoising autoencoder, they achieve very similar goals but in slightly different ways. One difference, of course, the denoising autoencoder is slightly easier to implement, because a small change, a few lines of code need to be changed, just adding some noise to the input in the case of denoising autoencoder. On the other hand, the contractive autoencoder, you have to penalize the entire Jacobian, which is a bit more complex. Now there's a third type of autoencoder which is called variational autoencoder. Now all the autoencoders that we discussed so far, they create a deterministic hidden representation. The variational autoencoder is fundamentally different because it creates a stochastic hidden representation, and the output is really, the hidden representation is really a sample from this stochastic representation. So what you're trying to do is that your objective function, it has two parts. One is the reconstruction error of the sample. That is, in all types of autoencoders, you always have the input to output, there's a reconstruction error. And the regularization term, what it does is that your hidden representation is really a distribution. So this distribution will be Gaussian with a certain mean and a standard deviation. And your regression term will push the parameter, the mean and standard deviation of the Gaussian specific to this data point closer to the unit Gaussian. It will obviously, if you regularize too much, every point will be represented by unit Gaussian, so then you won't be able to reconstruct. So in all types of regularization, you always have this trade-off between the reconstruction and the regularization. So let's look at how this is done. So essentially, the hidden distribution is pushed towards the Gaussian with zero mean and unit variance over the full training data set. However, if you look at a specific input x bar, where x bar is a vector, the conditional distribution on a specific input point x will be a Gaussian with its own mean vector mu x and its own standard deviation sigma x. Okay, so the encoder, it will output this mu x and sigma x, and then it will take a sample from a Gaussian with mean mu x and standard deviation sigma x to create samples for the decoder. And so essentially your autoencoder now, it has a stochastic component because your hidden representation is being created by sampling from a Gaussian with mean mu x and standard deviation sigma x. Now this regularizer here, it will compute the KL divergence, because what happens is the conditional distribution specific to this training point will be different from the unit Gaussian, which is what you want it to be close to. So the regularizer will try to push the distribution conditional on the specific point x closer to the unit Gaussian. So let's look at the architecture. So this is the stochastic architecture which has deterministic input. So essentially what is happening is that you have this encoder network which will create a mean vector and a standard deviation vector. This mean vector and the standard deviation represents the Gaussian which is conditional on this specific input. So you see this specific input over here on the left hand side, and there's a mean and standard deviation which is specific to this input, and you will be taking a sample from this Gaussian with this mean and standard deviation vector to create the hidden vector, and then the decoder will reconstruct this. Now the problem with this autoencoder architecture is that there is a sampling with operation, and you cannot back propagate because the sampling operation is not a continuous operation, it's a discrete operation, and you cannot back propagate. So the question is, how do you create a purely deterministic architecture which you can back propagate? So the key really here is that you reparameterize. How do you reparameterize? What you do is that instead of sampling from this mean and standard deviation, you generate some input samples. So you Gaussian samples from N0I. So from the normal distribution, from the unit normal distribution, you have some input samples. So you can see here I have this rectangle here which says Gaussian sample N0I. So you actually sample these upfront and you store them away. So they become a part of the input. So now you have done the sampling already, and now these samples become deterministic input. These are user generated input samples. So now you have two sets of inputs. You have input samples, and then you have the input data, which is an input image in this case. So the encoder now creates a standard deviation vector and a mean vector. So what you do is that now you multiply the Gaussian samples, you element-wise multiplication of standard deviation vector with these Gaussian samples. So and then you add it to the mean vector. So essentially what you're doing is that you are essentially creating a Gaussian with this mean and standard deviation to create your hidden vector. And then you have a decoder. Now note that what you have essentially done is that the sampling part, you have now made it as a part of the user generated input. So your entire network is deterministic because the stochasticity, you have generated it, you have now stored it away in the synthetic inputs. Okay, and this type of network now you can backpropagate. So now you can see the loss has two components. One component, of course, is a reconstruction loss, and the second is between this mean and standard deviation vector, you will calculate the KL loss with respect to the unit Gaussian. So that is also easy to do, and let's look at what the loss function looks like. So you have the reconstruction loss, which is exactly the same as all the other models. And then the regularizer is a KL divergence between the unit Gaussian and the conditional Gaussian. Now note that this conditional Gaussian is the mean vector for specific to this training point, and the standard deviation vector, which is sigma x, specific to this training point. So you can see this equation 6 gives you the regularization. Now, one thing you'll note is that if you look at the form of the scale divergence, the form of the scale divergence is such that it will be smallest. The regularization term will be smallest when the mean vector is 0. And similarly, it will push, if you look very carefully, if you work out the details, I will leave this as an exercise to you. This second term containing the standard deviation, it will be smallest when the sigma x goes to 1. So the regularizer is trying to push the mean and standard deviation towards 0i, but of course, because it's always a trade-off between the reconstruction loss and the regularizer, it's never going to push it fully to 0i. So the mean will again be sensitive to the specific input image you used, and the standard deviation again will be specific to the type of input image you used or the input data point you used. But the point, the more important point is that because you took away the stochasticity and you put them in user-generated input sample, now you can just back propagate through this network in a deterministic way. Now, let's look at how these three different types of networks, three different ways of regularizer are connected to, three different types of autoencoders are connected to one another. A variational autoencoder will regularize because stochastic hidden representation needs to reconstruct. So within a range of errors, within a range of noise added to the hidden values, you should still be able to reconstruct. So you can interpret this particular architecture of the variational autoencoder as adding noise to your hidden representation, because note that the user generated input samples, you can also interpret them as noise. So rather than saying that I'm sampling from this conditional Gaussian distributor, you can also say that I'm adding noise to this Gaussian representation in which the standard deviation vector decides how much noise I should add, and the mean vector is the average representation of the specific input. So now this type of adding noise, of course, here you're adding noise to the hidden representation. So, and you can interpret the mean as the representation and kind of standard deviation as the noise robustness of this hidden representation. But in the denoising autoencoder, you add noise to the input. So there's some difference in where you're adding noise to. And the contractive autoencoder is also resistant to the noise in inputs by penalizing the hidden to input derivatives. So the way in which the contractive autoencoder works that, okay, if I add some noise to the inputs, my hidden representation won't change. So essentially the hidden representation is robust to the noise. So in that case, the hidden representation makes muted changes with small input noise. So in all of these cases, you can see that the regularizer in one way or the other, it's connected to robustness to noise addition. Of course, they are done in slightly different ways, which is why they have slightly different properties. So let's look at that. So in denoising autoencoder, the noise resistance is shared by the encoder and decoder. The responsibility of noise, because you add noise to the input and then your output should reconstruct well. So often you use both the encoder and the decoder. So you often use it in denoising application. In contractive autoencoders, the encoder is responsible for noise resistance, because what you are saying is that I don't want my hidden representation to change too much. So if I change my input representation by penalizing the derivative, that's what you're saying. So often you tend to use only the encoder for dimension reduction. And in the variational autoencoder, the decoder is responsible for the noise resistance, because what happens is that you add the noise to the hidden representation. So if you look at this architecture over here, you can see that the user generated input samples, you can view them as noise, which you are adding to the hidden. So the mean vector is kind of like an average representation of your input, and your standard deviation tells you how much noise should I add for this type of input, and I'll be okay. And the KL divergence is ensuring that the kind of noise you add is closer to the unit Gaussian. But where you're adding the noise here is different, which ensures that the decoder is responsible for the noise represented. So the decoder is the most important part. So often with the variational autoencoder, you often use only decoder. So what do we use a variational autoencoder for? Well, it's very useful as a generative model. So typically what you do with a variational autoencoder is that you train it with the training data, and then you use it to generate images from the distribution that you learned on. So essentially what you'll be doing is that you will be feeding, so you throw away the encoder and you feed samples from the unit Gaussian to the decoder network, and it will generate different types of images. And these different types so imagine you have an MNIST data set, you trained it on the MNIST data. So often it will generate images of different digits. So there will be different variations on the digits because they're handwritten digits, and some of those digits may not occur in your original data set. They'll be like the images in your original data set, but they are small variations on the images in your original data set. This type of approach is also used in generative adversarial networks for generating fantasy images. So variational autoencoders and generative adversarial networks, they are two solutions to similar kinds of applications. Now, one question, of course, that arises is that why is this type of approach possible only for variational autoencoder, using the decoder to generate images? Why can't we just pick hidden representation, just sample hidden with other types of autoencoders and generate images? One reason for this is that the way in which you regularize the hidden representative, you force the hidden representative in such a way that over the whole training data it will be closer to the unit Gaussian. So sampling from the unit Gaussian will often give you meaningful images, will often output meaningful images. So if you trained it with a regular autoencoder, what could happen is that the latent representative that it will create, if you didn't use this particular type of it will have lots of discontinuities in the hidden space. So this is here I show a 2D latent embedding. Imagine you had an autoencoder with just two hidden units. So I'm showing a scatter plot of the data. So there are these regions in the space where there are no data points. So if you happen to sample from those regions, let's say you trained it on an MNIST data set with 4 digits. So you would get these 4 digits corresponding to these 4 digits, the different digits occurring at different points in the space. But if you sample from one of those points which is sparsely populated, you may not even get a meaningful digit. It may not, what you reconstruct may not even be a meaningful point. Whereas in the one with the variational autoencoder, the one I show on the right, no matter where you sample it from the unit Gaussian, in most regions you will get a very meaningful kind of image. One very interesting observation about using this kind of generation is that if you walked from one region in the latent space to another, so for example, if you look at the image on the right, so let's say these are 4 different digits of MNIST. So the plus, let's say the plus corresponds to a 4 and the stars correspond to a 7. So let's say you walked from the plus to a star. What you'll see is that the different images, so along this line, the 4 will gradually change to a 7. And in fact, at the boundary region, there will be a digit. Often it will look like an image which one would get confused between a 4 and 7. And such digits, they do occur in the MNIST data set. And in the case of the variational autoencoder, when you generate images, you will occasionally get these kinds of images too, which may not occur in your original training data. Now, this kind of application of variational autoencoders and generative adversarial network, they were proposed around the same time. And in fact, you can also develop conditional variants to fill in missing information. So you have conditional generative adversarial networks and you have conditional variational autoencoders. So you can use it for all kinds of translation. You can use it to fill in missing holes in images. You can fill in for image to text translation, text to image translation. So all these applications, the details of all these different types of applications, they're discussed in the book. But in general, generative adversarial networks, they tend to give you higher quality results as compared to variational autoencoders.